I hope now is in the full screen mode. Is that
Yeah,
right?
the screen is visible. So
Okay.
thank you so much for coming and agreeing to giving the talk. So yeah, we can start. Thank you.
Okay. Thank you very much for the introduction. And I'm Koki Tokeshi from Institute for Cosmic Ray Research in Japan, which is located next to IPMU actually. And yeah, today I'm going to talk about multiple field inflationary model, which respect OD symmetry, where the stochastic effects can play a crucial role. And this talk is based on our recent work with him. So before explaining our setup and the results, let me start with a very brief introduction about cosmic inflation. So today, we know that the observation of the cosmic microwave background, CMB, tells us that our universe is filled with background radiation, with the temperature being about 2.7 Kelvin, as well as very, very small fluctuations superposed on it. But this very isotropic background radiation seems not so natural in the sense that if you look back at the history of the universe, you will face with kind of fine-tuned initial conditions. So yeah, this figure schematically shows the so-called horizon problem, which is one of the fine-tuning issues in the standard hot Big Bang theory without inflation. So today, the relevant scales are coming inside the horizon, but if you look back at history, those scales comes outside the horizon, which means that a light coming from one direction and another direction cannot have a causal contact in a very early universe. So to explain this kind of a very isotropic radiation, we should admit the very, very fine-tuned initial conditions unless we introduced inflation. So this originally motivates to the invention of the cosmic inflation, and nowadays, presumably the simplest mechanism to realize inflation is to implement a single scalar fields, yeah, like that. So we did this kind of Lagrangian with general relativity as well as scalar fields in some potential. So this figure shows yeah, schematically the evolution of the scalar field. The yeah, for instance, the scalar field, or yeah, this is so-called the inflaton field. Yeah, for instance, the scalar field starts from very, very slowly rolling down on this potential. So yeah, you need very flat region on the potential. Yeah, because yeah, so that's the kinetic energy of the inflaton can be neglected, and the Hubble expansion parameter is approximately related to the potential. And since this potential is very flat, this means that this Hubble parameter is also approximately constant. So the scale factor of the space-time behaves like an exponentially growing factor, which is nothing but inflation. And yeah, in this slower regime, the evolution of the scalar field is determined by this equation. So you can see that the time variation of the scalar field is basically controlled by the potential gradient, and the scalar field is dragged down the potential so that it basically descends on the potential until the end of inflation, where slower condition violate and the inflation, yeah, therefore ends. And yeah, for convenience, in what follows, I will use the number of e-folds as a time variable to write down all the equation motion. So yeah, that was all about a very brief introduction about inflation. And here I want to introduce a kind of non-perturbative approach to the inflationary dynamics, taking into account the quantum fluctuation. So the formalism is so-called stochastic inflation, and this stochastic inflation formalism is kind of an effective field theoretical treatment that describes the evolution of the large-scale coarse-grained fields in a non-perturbative way. So the central idea to construct this effective formalism is to split the field configurations in the Fourier space into the superhorizon modes and the subhorizon quantum fluctuations. And if you integrate out these subhorizon quantum fluctuations, this guy, if you integrate this guy, you will eventually arrive at the effective equation motion for this large scale fields. And you can see that, this potential gradient term again appears in the effective equation motion. This is the same as the classical treatment that I previously already showed. But now, in this stochastic inflation formalism, this second term also arises. So the evolution of the large-scale scalar fields is governed by not only by this potential gradient, but also this stochastic noise with the amplitude h over 2 pi also controls affects the evolution of the scalar fields. This term comes from the quantum fluctuation because during inflation, quantum fluctuations are generated originally deep into the horizon, but as time proceeds, those fluctuations stretch due to the cosmic expansion and cross out the horizon at some time to become a part of large-scale fields. So this is why this stochastic noise affects the evolution of the large-scale scalar fields, like in this way. And this is the expressed expression for the stochastic noise. And the one-time derivative hits the cutoff function. This is Heaviside theta. So that's the relevant modes at each time that cross the horizon can only contribute to the dynamics of the large-scale scalar fields. And since this stochastic noise comes from quantum fluctuations, the mean is vanishing, and also the covariance takes the form of the delta function, which means that this stochastic noise is white noise with the Gaussian distribution. And this figure shows a physical meaning of this, this stochastic differential equation or Langevin equation. So you can generate many stochastic realizations by using this equation. And each realization corresponds to the evolution of each hyperpatch during inflation, as this figure shows. So the fact that the evolution of the inflaton field is governed by this Langevin type equation motivate us to derive the evolutionary equation for the distribution function of these scalar fields. So, for instance, if you start from some given initial condition, this inflaton field basically descends on the potential. But due to the presence of stochastic fluctuations, the evolution of the scalar fields becomes random. So the location at a given time n is promoted to a stochastic number. So the location has a corresponding distribution function, this f. And this is governed by the Fokker-Planck equation. So the solution to this Fokker-Planck equation f describes the distribution of the field value at each given time n, starting from some initial condition, initial time. And another important distribution function is a solution to the adjoint Fokker-Planck equation. Because, again, due to the presence of stochastic fluctuations, the duration of inflation, I mean the time from the initial location to the end of inflation, where the slower condition violates and the inflation ends, is also promoted to a stochastic number. And this duration of inflation has a corresponding distribution function, which is the solution to the adjoint Fokker-Planck equation, like this. So the former shape is very similar, but the meaning of the solution is very different. And more important one is this adjoint Fokker-Planck equation, because in this talk I want to calculate the mean number of E4s, which can be obtained by multiplying the number of E4s n to this equation and integrate and so on. So those Langevin equation and Fokker-Planck equations and as a central equation motion in stochastic inflation that will be solved to determine the stochastic evolution of the inflaton fields. So now let me move on to our setup. So the situation that I want to focus on in this talk is inflation driven by multiple scalar fields. So here D represents the number of scalar fields that contribute to the inflationary universe. And for simplicity, I impose all this symmetry in the field space. So the field space is rotationally symmetric. This imposition is for kind of simplification and also whole analytical treatment to the following discussion. Sorry. So because of all this symmetry, all the relevant physical quantities depends only on this radial displacement of the field. This is the only degrees of freedom that is relevant to your system. So I'm here introducing the non-dimensionalized fields, which is defined by the absolute value of the field vector divided by the reduced Planck mass. And I also introduce the non-dimensionalized potential, which is defined by the dimension full potential divided by the reduced Planck mass to 4. And this picture shows a very simple example where only two fields derive inflation, and also without stochastic fluctuations. So this black straight line describes it's a solution to the classical equation motion without taking into account the stochastic fluctuations. So the horizontal and vertical axis are the field. And if you start from some initial location, it basically rolls down on the potential towards the end of inflation surface. And the concrete input to generate this example figure is a quadratic double field potential. But remembering that I'm imposing all this symmetry, in this case, the two masses must be identical. So this is the classical trajectory, but once you take into account the quantum fluctuations, so stochastic fluctuation, which appears as a random noise term in the Langevin equation, the field space trajectory can, in general, deviate from the classical straight line. So you can guess that the total duration of inflation, I mean the time from this initial location to the end of inflation surface, is extended because of this detour occurred by the stochastic fluctuations. So I want to give an answer to the following question. What is the number of field dependence of duration of inflation? This stochastic mean of the duration of inflation. Because as I explained using this figure, if there are multiple fields, there can be loitering behavior in the field space because of the stochastic fluctuations, and this gives rise to the extension of the extra number of E4s until the end of inflation. So this extra extensions number of fields is expected to contain some information about the multiple field effects. So this is why I want to give some answer to this question. What is the number of field dependence of the mean number of E4s? So to tackle this question, let me start with the adjoint Fokker-Planck equation, the solution to which describes the distribution of the duration of inflation. So by multiplying n to the both sides of this adjoint Fokker-Planck equation and integrating, and maybe by integration parts twice, you can obtain the analytical but formal expression for the stochastic mean number of duration of inflation. So yeah, the reason why I said this is formal is because this expression contains a double integral, which cannot be carried out analytically in general. And here I must explain the two boundary conditions because those two boundary conditions appear in this expression since the adjoint focal-Planck equation is of second order in the spatial variable, the fields. So the first boundary condition is the absorbing boundary, which is located at the end of inflation surface. So yeah, here I'm assuming that once the inflaton field touches this absorbing boundary, it never going back to the inflation region. And the other boundary condition is reflective boundary, which is often praised, yeah, formally in some cases. So this reflective boundary is placed in some very, very high potential region to prevent the field excursion in the, for instance, Planck scale. But in this talk, since I will focus on the so-called small noise regime, the exact location of this reflective boundary becomes completely irrelevant. Because in small noise regime, starting from this initial location, this inflaton field is basically dragged down by the potential drift towards the end of inflation surface. So if the noise is small, this inflaton field can hardly ascend the potential. So this is why reflective boundary becomes completely irrelevant in what follows. So what I want to do here is to perturbatively expand this mean duration of inflation, assuming the stochastic noise is very small. And the key idea is that in this second integral, the dominant contribution comes from the lower end of the integral because, yeah, if the noise is small, the field cannot approach the reflective boundary because it's located in a very, very high potential region. So this is why I expand the integrand around the lower end of the integral y equal x. So for instance, for this 2 over v factor, this is expanded around y equal x, like this way. And eventually, what I want to obtain is a perturbative expansion of the mean number of e-force, like this, and where each case order term is yeah, proportional to v2k. Yeah, because now I'm choosing this v, this non-dimensional potential, as the expansion parameter because in the small noise regime, I can assume that this guy is also small. So yeah, yeah, let me expand the mean number of v-force in small noise regime. First, we must check the consistency. I mean, at the leading order of the noise, or in other words, in the absence of the stochastic noise, the calculated mean number of v-force must reproduce the classically predicted, the well-known formula. And this is the result. Yeah, I should say that yeah, this consistency check is not a result, but it's already confirmed by some previous works. But anyway, as the leading order in the noise, the well-known formula that measures the Lebesgue number v-force is correctly reproduced. And in particular, if you assume the monomial potential, which depends only on some powers of the absolute value fields, yeah, again, the well-known formula for the number of v-force is reproduced. So this is our first consistency check. And in what follows, just for convenience, I'm writing each of the term of the number of v-force in the differentiate form because outer integral can be performed whenever after all the perturbative calculation has been finished. And Oh, yeah. And you can not observe the number of field dependence at the leading order in the noise because it depends only on the absolute value of the fields. However, when you go to the first order, the next leading order in the small noise, you can find the d-dependent term in the first order correction to the number of V4s. In particular, the d-dependent term at the first order depends on d in a linear way, d to 1. And another thing that we can observe from this expression is that the first order correction tends to increase the elapsed mean number of E4s, which is consistent with our intuition that stochastic effects tends to affect tends to affect the mean number of E4s in the increasing way by the loitering behavior in the field space. And this perturbative expansion can be performed in an arbitrary order in principle. And this is second order correction in the number of E4s, where you can see that not only the linearly dependent term, but also there appears quadratically dependent correction terms, both of which vanish in the single field limit. I mean, when d equals 1, those two terms vanish. And this again increases mean number of V4s. And basically what we should do is the same, but since this is a very good opportunity, let me show the third order term in the small noise, where you can find not only the linear dependent, quadratic dependent terms, but also the cubic dependent terms contribute to the extension of the mean number of V4s. So this kind of perturbative expansion in the small noise regime can be, in principle, performed in an arbitrary order, but without specifying the concrete expression for the potential. Expression becomes more and more complicated when you're going to higher and higher order. So here I'm restricting myself to the monomial potential, in which the potential is determined by solely by the some powers of the absolute value of the field. And in this case, we can derive the all-order expression to the mean number of V4s. So this shows case order correction to the mean number of V4s when you choose monomial potential. And by summing up all order expression, you can write down the all order perturbative expansion of the mean number of V4s in small noise regime. So this figure shows the mean number of V4s, this guy or this guy, as a function of the number of fields. You can see that at the leading order of the noise, at the zeroth order in our perturbative expansion, the mean number of V4s does not depend on the number of fields. And this is classical well-known results that I showed previously. And the remaining 5 curves, the higher order corrections or perturbative expansion, this analytical formula, as well as numerical dots for consistency check. And you can see that if the number of fields is not so large, like order 1 or 10 or even 12, the first order correction is sufficient to be along with the actual value. But when order of 10 or more fields are prevalent, only the first order correction is not sufficient to reproduce the actual value. You have to take into account the higher and higher order terms to know the actual value by this analytical formula. So anyway, this figure shows that the number of V4s is indeed extended when more and more fields drive inflation. And if you take a closer look of the perturbative expansion, you can find kind of a convergence radius like this. So this expression is the asymptotic expression of the case order correction term for large K. So if this convergence radius is less than unity, this perturbative expansion can be reliable, while if this convergence radius exceeds unity, the perturbative expansion breaks down and the evolution of the scalar fields transits to some non-perturbative phase. And from the converging condition using this convergence radius, you can find out the purely theoretical bound on the number of fields D, like this. So this gives the upper bound on the number of fields, and below which if the number of fields D is less than this upper bound, the this perturbative expansion can be reliable and inflation successfully ends, while if the number of fields D is more than this bound, this perturbative expansion breaks down and inflation cannot successfully ends. So you might wonder why this kind of upper bound or convergence radius exists. And the reason of why, the reason of existence of this kind of convergence radius can be known if you go back to the Langevin equation. So recalling that the system respects all this symmetry, so the effective degrees of freedom is just one. This is radial displacement of the field. So you can derive the reduced Langevin equation for this only one degrees of freedom, which is given by this form. So now it can be seen that the evolution of the radial displacement is controlled not only by the classical drift potential gradient, but also there appears a centrifugal force term, which originates from the stochastic effects, although it plays the role of deterministic force. This is because this potential gradient is order of v to 0, so this is a classical force. But this centrifugal force is order of v, from which we can see that this originates from the stochastic noise. In other words, if you do not take into account the stochastic effects, you do not find out this centrifugal force. And on the convergence radius, those two deterministic forces are balanced. And this is why there exists the upper bound as well as the convergence radius. So if the number of fields D is less than this bound, the classical drift force overcomes the noise-induced centrifugal force, which gives rise to the successful end of inflation, because on average, the E-photon fields rolls down on the potential towards the end of inflation. On the other hand, if there are too many number of E-folds that exceeds this bound, the centrifugal force term overcomes the potential gradient, by which the E-photon fields continuously ascends the potential. This means that inflation never ends and the universe transits to the phase of kind of eternal inflation. And things can be more transparent if you look at the effective potential. So this is, again, let me show the effective Langevin equation for the radial displacement. And this figure shows the effective potential as a function of the initial field value, which is defined via those two deterministic force. And let me explain using the situation where the number of fields is just 100. So the red dashed line here. And at some point, or for some initial condition, the effective potential, the derivative of this effective potential becomes 0, which means that at this point, the two terms are the classical drift and noise-induced centrifugal force balanced. So if the initial condition is placed for instance, around here, the inflaton field is dragged down towards the end of the inflation surface, which means that the successful inflation can be expected on average. On the other hand, if the initial location is placed around here, the induced force, noise-induced centrifugal force dominates the dynamics so that the inflaton fields goes to the right direction. In terms of the original potential, it continuously ascends the potential to realize eternal inflation. So in such cases, the evolution of the scalar fields cannot realize our universe. Yeah, this is actually exactly the same as the critical number of inflaton fields that I showed in the previous slide. And this figure shows, I want to explain basically the same thing for the situation where more and more fields are prevalent. So if you look at the black solid curve that corresponds to the situation where the number of field is 1000, you can see that the allowed range to realize our observed universe without eternal inflation becomes becomes narrow, which implies that if the number of fields is very, very large, more and more fine tunings is required for the available initial condition. Unless a universe goes to the eternal inflation phase, and our universe cannot be realized by this kind of multiple field inflationary scenario. So this is our result. And finally, let me summarize the talk. So in this talk, stochastic effects in the all these symmetric multiple fields models are studied. And as I explained, at the leading order of the small noise, no D dependence, the number of field dependence can be observed. But when you go to the higher order, there arises a number of field dependent terms, which tends to increase the ellipse number of fields. Ellipse number of E-force. And by going to higher and higher order and eventually obtaining the all-order expression of the number of E-force, the upper bound on the number of fields was found, above which the particle expansion breaks down. And that condition is equivalent to the situation where inflation fails to end. And several future prospects that I have in mind is the first one is that we are now calculating the variance, although in this talk I focused on the mean number of V-force, because together with the variance and the mean number of V-force, we can calculate the observables like the power spectrum of culture vibration as well as its spectral index. So we can see the multiple field effects in those observables. And we are now finalizing the paper. And another interesting direction might be to consider to loosen the symmetry condition. I mean, to consider non-OD symmetric situations. And in that case, we are expecting that the quantitative consequence remains the same, but it might be interesting to the effect of the small symmetry breaking on the number of V-force, such as a small hierarchy between masses of the inflaton fields. So that's it. I stop here. Thank you very much.